So I'll start by explaining, I'll start by stating actually that this talk is going to be mostly about event-related potentials, so responses to a stimulus and time log to that stimulus. And I want to explain why I'm interested in this. Well, obviously, the main interest in event-related potential comes from the fact that they are a relatively straightforward measure of the underlying cognitive function. They can be observed in passive tasks, though, which makes them a wonderful translational tools across species, for example, or across age, or across health and disease. So in terms of their stability, they're reasonably stable. Reasonably is a key word within subject, although there is lots of between-subject variability due to cortical folding mostly. And the interesting ERPs, for me at least, are those ERPs that do not require attention. So they can be modulated by attention, but do not require attention. And again, this links them back into this translational value of them. Okay, so the research I'm going to be talking about today focuses on sensory processing. And in general, we do sensory processing in two modalities, vision and audition. However, today I'm going to be mostly talking about audition. And I'll just add vision, sorry, and I'll just add a bit of audition at the very end. And the etiologies that I'm going to be interested in are MCI, mild cognitive impairment, and Alzheimer's disease. But I'll talk about healthy aging as a necessary control and also as a, population that's worth kind of looking into in its own right. So that's a very quick roadmap. I'll talk about early visual ERPs in healthy aging, then in MCI and AD, and I'll just conclude by kind of mentioning auditory ERPs in the same populations. Okay, so why are we looking at visual processing in dementia? Dementia is such a memory deficit. Why look outside memory? Well, the reason why we're looking outside memory is because this cognitive testing of memory is always too late. So looking at another domain is very useful, therefore, and moreover, there is lots and lots of demonstrations of visual deficits in in dementia. So, for example, visual orientation abnormalities are ubiquitous in dementia. There are problems in visual search and alerting, and actually there are studies that say, like the SCAWA study here, that suggests that it's not just a property that's present when dementia is kind of, present in people in its full form, that you actually can find visual memory deficits a decade before diagnosis. Well, alongside those visual processing deficits, there is actually very little interest in visual areas when it comes to pathology. So if you look at the macropathology in the visual cortex, usually that does not come until Braak stage 5 out of 6 in dementia progressing, which is quite late. However, it has been noticed that the reason for that could be that no one looks outside primary visual cortex, whereas visual association areas contain much more synaptic complexity and therefore might be subject to micropathology quite much earlier. So in this McKee study, they specifically looked at microstructural pathology, so in the absence of atrophy in visual association areas, so that's extrastriate cortex or BA19, and they found that in 100% of MCI and AD patients there was a micropathology. And actually, in fact, there was some significant amount of the same pathology in intact elderly populations as well. Okay, so that's the rationale for us looking into visual processing. So if we, using ERPs, we can look into components that originate in those visual association areas, and by looking at how intact or non-intact they are, we could explore more, we could potentially use them as biomarkers of the underlying disease. So the paradigm that we used in our study is visual oddball paradigm, and it's very simple. In a task, participants see 3 types of stimuli. A standard stimulus like this, where you have a single bar, which is interspersed with an infrequent deviant stimulus, and an equally infrequent target stimulus. So the participant's task is to respond to a target. The deviants and standards are kind of unattended. And the ratio of them in our case was 16 to 1 to 1. So just to exemplify, it looked like that. So standard, 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 deviant, standard, standard. The ratio is not quite the same here. It's not 16 to 1, but just to give you an idea. So what we're looking at the response to the event, and the response to the event, to a visual event, and response has a very prototypical morphology demonstrated here from the young population. So you can see a very prominent P1 response, a positive peak followed by a negative N1 response. By the way, what I'm plotting here is an average of 7 occipital electrodes, but those are electrodes that pick up the responses most strongly. So the P1 and N1, their origin is quite well known. Both of them are thought to originate in the extrastriate cortex. These are details on their timing. And what's important is that we kind of have an idea of what they represent, what kind of function they represent. So in case of P1, this is still within basic visual processing. So if you know, as you know, a visual object is decomposed and then needs to be recomposed. So like P1 has still stages of recomposition of this visual object. And then N1 is a later stage that reflects visual spatial attention and object level processing or categorization. So what I've done here now, I've added I've added the line from the healthy older population. So we're comparing 25-year-olds to 75-year-olds here roughly. And what you can see right away, so looking at the P1, you can see that the amplitude of P1 is hugely reduced, and also its morphology has changed from a single peak to a double peak. Just like that bit just makes it clearer and enlarges this. So the reduction is probably most likely is probably due to the impoverished sensory input in older adults. Although all of our adults had corrected or normal or corrected to normal vision, nevertheless there is a wealth of studies like electroretinogram studies suggesting that even then the input from the retina to the cortex is weaker gets weaker with age. The double peakness of the P1 is very interesting though. So we think it represents desynchronization of multiple processing that normally go into the normally happen in the P1 window. So the timing of those processing in the young brain is close enough to coalesce into a single peak. In the aging brain, those processes are desynchronized, and as a result of this, we see this bifidness of the peak. Just to show you that this might be a sensible hypothesis. So what we're looking here, we're looking at the time frequency domain. So we're looking at the same responses, but now in the time frequency domain. And so what it is, what this lower panel represents is the difference between double-peaked and single-peaked P1 responses. What you can see here in the gamma range is the increased activity in double peakers compared to single peakers. If you know, gamma activity often is thought to represent binding of various properties. So we think that in the case of double peakers who exhibit problem in synchronizing those properties in the first place, this extra gamma activity is actually a compensatory activity needed to bind the object. So if we talk about the translational benefit of this, can double peak be a sign of aging, for example? Well, we need to look at the individual subject data, and that's what we've done here. So to our probably surprise, but also pleasant surprise, we could see P1 peak pretty clearly in every single subject data. So we're looking here at the standard responses, and we had quite a few of them. So we had above 600 of them. But you can see that it's quite easy to spot, peaks in individual waveforms. So what's done in this slide, we've classified them into single peakers, young group, and single peakers in the young and old group, and double peakers in the young and old group. And I present the numbers here. So you can see that about 42% of all older people have this double peak morphology. This is a new finding for the aging literature, but it's not a new finding in the literature overall, because that pattern has been reported previously in relation to multiple sclerosis. So there, this double peaking was obviously taken as a sign of demyelination. However, what we want to point out is that that finding, which is used clinically, might be a bit misrepresented, and perhaps at least this could trigger further inquiry into the etiology of this response. Okay, so that was about P1. Going to N1 window, we can see that despite that impoverished and desynchronized input or the desynchronized processing, the N1 component is actually the same. And you might be surprised here, but what we should be looking at is at the like we're looking at the peak-to-peak difference between P1 and N1. So we're kind of rebaselining this, and that we think relates to it shows the age-related compensation that's much talked about in the visual domain. So there's lots of fMRI evidence for age-related compensation in vision. This is like the equivalent EEG evidence. So this is just a summary for healthy aging. That's the pattern that we see in the healthy aging: reduced and double peak P1 followed by maintained N1 activity. Next, I want to talk about MCI. Now that we have the healthy aging baseline, we can talk about MCI and AD. This table on top gives you the details on our groups that we've used and their cognitive scores, so mini-mental scores. It's important to note that all of our groups, including the AD group, was medication-free. So we've tested our AD patients on the day after their diagnosis, which makes this data valid for making for use for diagnosis purposes, right? So early AD diagnosis. And these are the outcomes of the visual task from the older group, MCI group and AD group. This color scheme will be consistent, so you just can remember it perhaps. So I'll be looking at the P1 window first, and while we're in this space, I can just demonstrate, draw your attention to the fact that we see the same double-peaked pattern in MCI and AD groups as well as in the older group. But what I'll do next, I'll basically just present you the bar charts for the amplitude in the P1 and N1 windows for each of those groups. And this is what it is. So we're looking here at at the P1 amplitude first, and what we can see that the amplitude of the P1 amplitude was significantly different in the AD group compared to the older adults, but not in the MCI group. In the N1 though, there is a two-step progression. So the N1 gets reduced in MCI and gets even more reduced in AD. So we wanted to see whether this pattern is stable, right? So in order to even talk about this as being representative of the disease, we wanted to know how stable it is. So what we did next, so what we are looking at here are responses to the standard. So I'm going to show you the same pattern, but now I'm going to plot deviant and target stimuli in addition to standards. And that's what's done here. So we have the same plot, standard plot as in the previous graph here, but now alongside with deviants and targets. And you can see that this pattern of maintained P1 in MCI, but reduced P1 in MCI, in AD, is present not only in the standards, but also in deviants and targets, which are 40 times as numerous. So here we're looking now at 40 responses per subject, which is actually very easy to conduct, in terms of just data collection. And again, so not only the pattern holds in P1, it also holds in N1. We can see that there is a reduction in N1 for both MCI and AD patients compared to the healthy older adults. Okay, so that's one way in which we can kind of verify our pattern. This is another way in which we verified our pattern, although this is much more suggestive, and actually I'm saying this explicitly on the camera, this stuff is just trends, okay? But so what we've done now, we've looked at our MCI group, and we thought, okay, if that were true, what we would expect, if we had their if we had their the information on their disease progression, that could be interesting in terms of as it would allow us to split this group into MCIs who progress to dementia, and in this case we would expect them to be closer to this green bar here, and MCIs who are stable, in which case they should be closer to the yellow bar, to the orange bar. And that's exactly what happened. So we could only collect the information from 19 patients, so this is totally underpowered. Our MCI stable group is tiny, and it's only 7 people. But nevertheless, with all due caution, what we see here is that the N1 responses were exactly the same across, for both MCI groups, whereas P1 responses differed. So MCI responses from the P1 responses from the stable group were closer to the healthy ones than from the converted group. So what we see, so far I haven't explained anything. What I've just done, I've just shown that time after time, the P1 goes, the N1 is reduced in both MCIs and ADs, and P1 is maintained in MCI, but reduced in AD. So where can it come from? Well, we think we link this to the micropathology that goes on in the extrastriate cortex. So in the extrastriate cortex, the later processing goes first, basically. So the N1 responses, the object level processing deteriorates first, and then as the disease progresses, that kind of percolates down into earlier stages of more primary basic visual processing. Okay, so one final way in which we could test whether the pattern that we're talking here is really specific to AD and related to micropathology is to look into a different domain. So, and we have this domain, we have data from the auditory domain from the same people. So what we're looking at here, we're looking at auditory responses now from the same populations of older MCI and AD patients. And what we're looking here, what we're interested in, we're going to look at the first, I don't want to call them equivalent, but the first two strong ERPs in the auditory domain that could be thought of as equivalents in terms of when and how they occur to the visual components that I've talked about. And so looking here, so what you see here is a summary of P50 response and N1 response for the old MCI and AD groups. And there are absolutely no differences in either component. So the auditory processing is preserved. The visual processing is deficient in AD and somewhat in MCI. So we think that this gives us a better reason to claim that this P1 and 1 pattern in MCI indeed could be representative of the micropathology in extrastriate cortex. Okay, so that brings me to the final part of my talk. So what's next? Well, so I've been talking just about ERPs today. We're planning, so if we were to use ERPs as part of the diagnostic tool, that would be only sensible to use them alongside other types of EEG data. So we've had a few talks today about resting state EEG. So actually part of the research that we're doing now is to look at the resting state EEG from the same patients in the hope that together with the ERPs, they would provide a more integral diagnosis tool or like categorization tool for MCI and dementia. And that's done in collaboration with Mark Goodfellow, John Brown, and other people at Exeter. The other thing that I wanted to mention is another type of ERP component that I haven't talked about, but which I'm very interested in, called mismatch negativity. And that's the negative deflection to the unattended deviant stimulus in this oddball paradigm that I've demonstrated. So that mismatch negativity is known to reflect a change detection. And so what's interesting about mismatch negativity is that it's a very smart component. So it has been shown to correlate with the cognitive function across many etiologies and many diseases and many kind of healthy states. So roughly, if you have, if your mismatch negativity goes down, your cognition also goes down. And I'll show a bit of this in the next slide. The reason for this relationship is thought to be due to the fact that the mismatch negativity is basically supported by MNDA receptor function. So with the deficiency in this function, mismatch goes down. That's a kind of EEG correlate of cognitive function more generally. So this kind of relationship has been shown to be present. 5 minutes. Okay, perfect. So the relationship between mismatch negativity and cognitive function has been shown in Alzheimer's and MCI, so by those authors and some others. So here's what we see in our data. So indeed we see that mismatch negativity in the visual domain, for example, here is linked to the cognitive status of the patient. So what I'm plotting here are each of those dots is an individual participant, and on the x-axis is their mini-mental state exam score, so their some kind of cognitive function measure. And on the y-axis, this is the visual mismatch amplitude, And you can see that there is, a significant, probably not massively significant, but nevertheless significant relationship between those two. The relationship becomes much more significant once just the AD patients are taken into account, probably because we're looking at the ceiling effects in the MMSE scores in the healthy older aging. In the auditory domain, our mismatch paradigm was set up such that our deviance and standards were presented with a very short interstimulus interval, and that's known to be not a good condition for eliciting mismatch problems kind of in diseased populations. But even so, what you can see is that we had the mismatch, and that's the mismatch window. So basically, I'm looking at the difference between the standard line and the dotted line here, plotted as a bar in each case. So the mismatch negativity was higher in the older populations than it was in MCI and AD. This difference was highly significant for the old to MCI comparison, and that was just a trend in case of older and AD patients. However, as I've said just now, we think that our elicitation conditions were not ideal. So in our future research, hopefully, we'll set up a paradigm that allows to tap into this with a better granularity. So to summarize, we found what we think could be a potential biomarker of MCI and AD in the visual domain. So in terms of P1 to N1 pattern, specifically the P1 and N1 are both reduced in AD, and P1 is maintained while N1 is reduced in MCI. So we think that this could be a disease progression stage in which extrastriate pathology develops gradually and affects first the later stages of visual processing, and then as it progresses, even more basic stages of visual processing. And mismatch has potential as a translational marker of cognitive functional. That's at least what we want to explore. And thanks to all of our funders and to you for listening.
Thank you. Time for a couple of quick questions. Peter.
Okay, I need to summarize all of this. So let me summarize as I go along. So basically the suggestion was to look into alternative explanations for the P1 findings that we've got, right? Or to kind of explore it a bit more. In terms of phase locking, we're definitely doing this. So we have not found any phase locking differences. No. But we must say that phase locking, even in the healthy populations, phase locking, like in P1 in healthy populations, is not an explored area. So we don't have a good baseline there. You're probably thinking that, well, since we have this desynchronization, we should be actually better off picking out differences. But I think that's.
Normally, you always have a strong phase lock response to a prominent visual.
Oh yeah. Sorry. In that sense, I misunderstood you. Yes, of course we have it. Yes. So, and that was shown in one of the slides here. Oops. Yes. So this is the strong phase locked response, which we can see.
But it's only power that you're plotting there. Phase
oh, sorry. You mean the phase locking factor, basically? Yes. Yeah, okay. So we haven't found any differences there between double peakers and single peakers. So actually the only thing that we found was this difference in the gamma response later on. But I can see, I agree with your logic, it was surprising there wasn't. As for your second point, which was about
the latency jitter.
So the latency jitter of P1, so what do you mean by this? Do you mean individual subjects?
Yeah,
but if it were just just a jitter, right, you would expect it to be present in both groups, right? So you have to agree that this is a jitter that's specific to the. Well, it still leaves us with the differences, like aging differences, right? So the jitter was, let's say I agree with you, it still is the case that we need to explain why there is more jitter in the aging populations than in the MCI and AD compared to the healthy aging, right? So we did look so we did not record eye movements, but we did have the same question from a reviewer actually who asked
wasn't
about
me.
skates. Well, so we cannot rule this out as a. I mean, the only way we can rule this out is by having eye tracking alongside, basically. So for now, I have to just basically accept that this could be a confound.